Level 1, Chapter 2, Atoms, Molecules, and Ions. First, let's talk here about the atomic model. So we have 5 different types of atomic models, right? And the first one, Dalton's atomic theory. So according to the theory, all elements are made up of tiny indivisible particles called atoms, which can neither be created nor destroyed during a chemical reaction. And then all atoms of a given element are alike, but the atoms of one different from is different from another one, another different elements. But he still needs some work. He needs some work here. So the elements of the same atom are alike, but yes, different elements, they are not alike. They are different, right? Compounds are formed when atoms of different elements combine in a fixed small whole number ratios. And we have it when two elements combine to form more than one compound. That's different but definite whole number from whole number atom ratio for each element. When a chemical reaction occurs, atoms from that substance reacting with another to form a new different substance, have different combinations of atoms, but the atoms are not created or destroyed. So they are the same, for example, here, right? We have initially hydrogen with oxygen. So in ordinary reactions, the hydrogen and the oxygen should be here still, like here, right? Hydrogen and oxygen. That combined, they're gonna produce in here, it's making water, right? And you're soon gonna see that when we have a chemical reaction, we need to balance the reactions. So that it means balance means the same amount of each element should be the same in the reactants and products, right? So here you have two hydrogens, but here you have two oxygen, and here you have only one. So we're gonna do here, that's gonna add 2. And when you add 2 here, you 2 oxygens, perfect. But when you add the 2 in front, you are also changing the amount of hydrogen. 2 times 2, 4. So we need to add 2 here to be 4 hydrogen as well. That it says here. In a chemical reaction, the atoms from the start react with one another to form new different compounds, have different combinations of the atoms, but the atoms are not created nor destroyed. Okay, so 5 different kinds, 5 different models here. The first one, Dalton, he thought the atoms was a solid sphere. He recognized that atoms for particular element is different from another element here. But the negative one was he thought that atoms are divisible, but are not, right? So the atoms, you know that they have subatomic particles, but Dalton didn't consider the subatomic particles. The next one, Plotting model, Plum pudding model here, Thomson, he thought that the atom composed of electrons throughout around here, and you have a spheric positive cloud of positive charge. So positive charge here, and the round electrons around. So it looks like a pudding here. The positive one recognize electrons as composition components of atoms, but he said that he did not talk about the nucleus, so did not explain later, did not explain about anything about the nucleus here. Nuclear model is Rutherford. So he did a test with firing positive alpha particles in a thin gold in a gold sheet, and some particles pass through and some particles deflect. So why that happened here? So this that happened because this was only possible if the atom was mostly empty space with a positive charge in the center, that's the nucleus. So he knows, okay, you have empty spaces here, right? And the center have the nucleus. That's why some was deflecting and some was passing through subparticles. Okay, the positive thing was, okay, he realized positive charge was localized in the nucleus of an atom, but did not explain why electrons remain in orbit around the nucleus. Okay, so here, orbits. And then planetary model. Okay, we still talk about our orbits here, right? According to Bohr. So the Bohr here is a modified Rutherford model of the atom. So stating that electrons move around the nucleus in orbits at a fixed size of energy. And electron energy is this model, and this model was quantized here. And you have it here. So the the nucleus is still positive and electrons in orbits. The positive thing here, the proposed stable electrons orbits explain the emission spectra of some elements. But in the negative was like moving electrons should emit energy and collapse into the nucleus. So that the model did not work well for heavier atoms. Do not explain, because if you have heavy atoms, the electrons around will collapse to the nucleus here. Right, so the last accepted model, this one, we are using today as accepted model, still quantum model. So the state is there, the scientists here, the electrons do not the electrons do not move in orbits around the nucleus, but in waves. And it's impossible to know the exact location of the electrons. So what we have clouds called orbitals, that it has high probability to find the electron in the orbitals. These electron clouds are called orbitals. Okay. The positive, so shows electrons don't move around the nucleus in orbits, but in clouds where their position is uncertain. And it's still, the model here is still the accepted model. Right. So atom, molecules, and ions. The atom, all of the elements listed in periodic table are made of atoms, right? An element is the smallest particle of an element that retains the characteristics of that element. For example, aluminum foil consists of atoms of aluminum. Okay. So then you have the atoms, you have protons, neutrons that are in the nucleus, and electrons that are outside the nucleus. And the symbol for proton, P or P plus, in a charge is a positive charge, and the mass of proton is 1.07. That in the location of the proton is the nucleus. And neutron, the symbol is N or N0. There is no charge for neutrons. The atomic mass unit is around the same as the protons, about 1.08. The location of the neutron is also in the nucleus. Now, electrons. Electrons is a symbol is E with negative, right? The charge is negative, and the mass is very, very small. It's 0.0055. So it's very, very small. And the location of the electrons are outside the nucleus, is outside the nucleus. Atomic mass units, AMU. So the atoms, they have very, very small particles, right? And they have still no atoms that have mass around this one. 4 times 10 to the minus 22 second, that means very, very small. Oh, 4 times 10 to the minus 22 grams. So very, very small here. So you start, okay, let's use a scale. What's the scale we're gonna use? Like this. Instead of to be expressed in grams, I'm gonna use it AMU, atomic mass unit. Atomic mass unit is 1.66054 times 10 to the minus 24 grams. That means if an element has atomic mass like 12, in grams it would be 12 times this amount here. Right, so problem 1, true or false? The mass of the electron is greater than the mass of proton, true or false? So here, so that the proton is actually much, much larger than electron, that means this for the statement here is false. Then you have protons have a positive charge, and the electrons have a negative charge, so you know that is true, right? In the next one, the nucleus of an atom contains only the protons and neutrons, okay? Then subatomic particles here. How do we differentiate between different elements? It's by the atomic number. Each element has atomic number. So the number in the periodic table above each symbol is the atomic number. And all the elements, they have the same atomic number. Like we have different kinds of carbon. Carbon 12, carbon 13, carbon 14, but all carbons will have atomic number 6. And the number, atomic number is the number above the symbol of an element in the periodic table, right? So if the atom is electrically neutral, the net charge is 0, so the numbers of protons is equal to the numbers of electrons. For example here, right? So I have this problem in here. Sodium, zinc, and sulfur, right? So we have atomic number, numbers of protons, and a number of electrons. We get in the periodic table. So periodic table here. Sodium, the atomic number for sodium is 11, right? Sodium 11. So atomic number is 11. Numbers of protons is the same. In electrons is also 11. Number of electrons. So the atomic number is the same number of protons, right? Next one, zinc. Zinc atomic number is 30 here. So zinc has 30 protons and 30 electrons. Okay, so we need to understand how to read the periodic, the symbol, right? So isotope symbol of carbon, so have this symbol right here. Then on the left top here, have the mass number, the number of protons plus neutrons, we write it here, right? Numbers of protons plus neutrons, that is mass number. And the number here on the bottom, the left here, the atomic number. Atomic number is the number of protons, right? And if the atom is neutral, it will be also the numbers of electrons. So mass number represents the number of particles in the nucleus. Is equal to numbers of protons plus neutrons. So the mass number does not appear in the periodic table because it applies to single atoms only. Okay, so how to calculate the number of neutrons in the atom when the mass number and the atomic number are known? So we know what we know about numbers of protons is equal to atomic number, right? And what to know about the mass number? The number of protons and the numbers of neutrons plus numbers of neutrons is equal mass number, correct? So to find the mass of neutrons will be a subtraction between the mass number, right? Minus atomic number. All right? Okay. So I'm going to stop here for chapter 2, part 1.